Good morning. I suggest we get started. So I hope that we will have time to do as many exercises as possible. We'll see how it goes. But of course, feel free at any moment to kind of keep on typing with me. When we'll kind of formally stop and do exercises, what I'll also ask you to do is to use the two sticky notes to call me or one of the TAs if there is an actual problem, this one, but also whenever you're happy with the exercise, whenever you have finished the exercise, or even though you haven't finished it, but you understood what the point is, you're confident you could do it to the end, even if you don't want to actually do it, then please use this sticky note, put it on your laptop, so that I can also see an overview of the general progress of the classroom to know when we can move on, so as to not waste or wait for 10 minutes when actually you're all ready to move on. All right. There is, okay, let me open our studio here. I will assume that everybody is familiar with our studio. And what I'm going to do is that I'm going to create an RStudio project for these 2.5 days. And for every session, or every time we change a topic, I'll create a new script and add it to that project. At the end of the course, I'm going to archive this directory that contains all the scripts, data, and figures, whatever we have produced. And I will put this R project archive on the shared Google Drive, so that you'll have a kind of write-up of all the notes that I take to take with you home. File, new project, please. Thank you. Directory, new project. Call it RViz. And what I'm also going to do, going to create 2 new folders. Well, I'll start at least with one new folder called Data here at the top. And so we will use a set of data sets to illustrate some of the concepts that we're going to do. And that's one of the things I'm going to start with now to introduce these data sets. It will be possible to download the data sets and generate them as we go on. But in the Google Drive, do you know the Google Drive? Have you seen the Google Drive? Okay. Well, in that Google Drive, I think there is a file called data.zip, and you can also download the data sets in there and move them to that data directory. So you can either do that like now, or we will download this data and kind of generate them as we go on. Script 1. And the last piece of information before we can begin. So we will use a whole range of R packages through these 2.5 days. They might not all be absolutely necessary, or we might not use all of them. Some maybe are more for kind of demonstration purpose. But if you get a chance, if you run that script, source that file and run that script, this should install all the packages required and a little bit more. But if you are familiar with R, and whenever we want to do something, you will recognize the error message saying that the package is not available, and you'll be able to follow up. Easily, quickly install it and follow up. Otherwise, if you run that script, you should be ready to go. Oh yes, and the last point, I'm going to write this URL here at the top. All the lecture notes are available at this URL here, bit.ly/biomolviz with an S. So everything I'm going to say, and actually much, much more, is available there. Whenever we do exercises, the answers are already available, are available there on that link. I'm not going necessarily to follow the notes religiously. We might skip something, we might change the order, but don't worry, everything is there for you to look at. So as a mean of introduction, what are we going to do during these kind of 2.5 days? So we're going to learn packages, commands about data visualization, but we are not going to focus, or at least with me, on the kind of communication aspect, on the kind of beautiful aspects on the plot of the plots that we produce. Stephen, at the end of today, will address this a little bit more, what kind of colors to use, what kind of symbols to use, labeling axes and so on. We are not going to focus on that. What we are going to focus on is things between we have some data and we need to communicate this. Before that, we'll need to understand the data. We'll need to do, very often, quite a bit of work to convince ourselves that these data are useful, that there is an interesting signal in the data. That includes visualization, of course, but that also includes manipulating data. So not everything that we will do that needs to be done in terms to visualize data is actually producing plots. It also means filtering data, kind of rearranging data, calculating summary statistics about data, running some algorithms like Pca on the data to then produce a figure. So these are the kind of things that we will also learn and not only focus on producing figures, even though that's the end product, of course. So there is visualization, there is manipulating data. Something else that is important is data structure. Data comes in many kind of forms, many shapes, and some of these forms lead themselves to some type of visualization, and other forms, other data structures lead themselves to other types of visualizations. So something else we are going to do is to learn a little bit about these data structures and also how to convert data from one data structure, one form, to another. Again, this will help us to more easily produce the visualizations that we need. So any questions? So here I have written a kind of a short plan what the goals are for these 2 days. Can everybody see what's written on this board? Yes, good. Can everybody see what's here? If I you would use that one, yes, and here too? Okay.
There's no trouble with reading this.
Okay. Well, I'll use this one, but I'll speak here. So the first thing that we need to do is to learn a little bit about these data sets that we want to use. Maybe in an ideal world we would want to have one nice data set that can illustrate everything, but I haven't found that data set yet. So there are a couple of data sets that we're going to use, and that's also what I'm going to use as an introduction to these different data structures that we have. There is also a section about a general overview of visualization with a focus on mass spectrometry and proteomics data. And I think that's the next thing I'll do, is to give you an overview of all kinds of plots that could be produced, that could be generated. And then tomorrow we'll then kind of focus on how to produce these individual plots. And then we have 2 sections about dplyr and ggplot2. That's related to the question I asked yesterday or the day before. And we will go through dplyr and ggplot2 because these are extremely important tools to do this data manipulation and do this data visualization. And so if some of you, and some of you are already active users and are very familiar with these 2 packages, please help when we do exercises please help your neighbors if they have questions. Of course, we are here to help, but very often peer instructions working together is the best way to learn something. If you are the person that gets help or the person that helps, that's an extremely good way to learn things. Okay, I'm not sure we'll be able to finish everything today. The two big chapters for tomorrow are one that I called Tools and Plots, and that's where we're going to see, for example, how to do Pca analysis and how to visualize that data, how to do a heat map, how to do k-means clustering. Again, we will not focus on producing beautiful figures, and some of them will be truly ugly. But the point is not to produce, or at this stage, not to produce a beautiful figure, but to produce, some data representation that can be used to sometime when we are happy, when we understood the data, produce a nice figure. But we won't have time to spend, half an hour on producing the big figure for the paper. That's not what we're going to do. And then there is also a section about, what is available in Bioconductor for mass spectrometry and proteomics. And there I will focus more on raw data. And finally, that's for Wednesday morning, we will have a section on interactive visualization. Right. So let's start with the data that we, with the data that we have. I'll introduce the raw data when we get there tomorrow at some point. So the first data set that we have is the IPRG data set. That's a spiked-in experiment where a handful of proteins were spiked in a yeast background. For those that were here last week, this is the data set that we also use for the intro class. That's also the data set that Olga introduced. That's also a data set I think they use in the other room. And the goal of this data set was to compare and contrast how different groups, how different people managed to identify the proteins that display differential abundances, different ratios, without, of course, knowing which spike-in proteins were. And kind of in a nutshell, the take-home message of this study is that, it's probably relatively easy to find those that are differentially expressed, but actually the price you pay for this, that means the number of false positives that you detect can be very high. So it's not necessarily a very easy thing to do. But we're going to use part of that data set, and that's called the IPRG data set. Let me write it up here, IPRG. Okay, so to read it, so that file is also available in this data.zip file, but otherwise you can directly download it, and all the download links start with bit.ly, and the data sets all start with biomet data, viz biomet data, and so this one is IPRG CSV. And it is a CSV file. The reason why the URL where it lives is very long and very ugly. So read.csv reads this CSV file. Generally, we use local files, and your local file, I think, is called IPRG summary run.csv or summary run 0. So this produces a data frame with 36,000 and so observations, 36,000 rows, and 7 variables. So let's have a quick look at this data set here. Names. So we have one column, one variable that provides the name of the protein. We have a log2 intensity. Let me control L. Yeah. We have log 2 intensity and intensity. We also have a run, or the kind of the mass spec acquisition, the sample that this protein was identified in. We have a condition, we have biological replicate, and technical replicate. So this is the information that we have for these data sets. This data set. Very long table and pretty narrow. And maybe a useful command here to familiarize yourself with this data set would be to look at the conditions available and technical replicate. And this produces this table. We have 4 conditions, labeled condition 1, 2, 3, 4, and 3 technical replicates A, B, C. And this tells us that we have pretty much the same number of proteins for each condition and technical replicate. So this is already a form of, as far as I'm concerned, a form of visualization. Even though we didn't produce a figure, this table, and we could, and I think with the exercise, I ask you to produce a figure that conveys that kind of information. But this already informs me quite a bit about the data set I have. So this data set, and here, this data set, let me do the following, that will be helpful. View IPRG. Yeah. Here it is, that is useful. And I'll try to is the font size large enough for people at the back? Does that work? Yeah, okay, I'm not sure it has increased by zooming in. But that's a kind of equivalent, what we see here is the equivalent of doing hat IPRG. We see a couple of those rows. And typically these kind of data sets, before I move on, are you familiar with the concept of tidy data? Blue sticky notes, if you are familiar with tidy data, and the other color if you're not familiar with tidy data. So the tidy data set is a data set that has been cleaned up and that conforms to the following kind of requirements. In each row, we have one observation, one observation, and then for each of these observations, we have done specific measurements. We have a set of variables, and so these different variables are recorded along the columns. And if we stick to that rule, that we have observations along the rows and variables along the columns, and we only have a single variable per column, then the result of that is that every cell will contain only one piece of information. And we can easily manipulate that data set. Take a subset of rows, and we know that these requirements, these expectations will still hold. We'll still have all our variables for these observations. And if we subset, for example, one column, one variable, we know that we'll have the record of all these observations. Sorry, all this variable, the values for all these variables for all our observations. Okay? An example of a non-tidy data set would be if I have a patient many patients here along my rows, and then I would have one column that says group dash sex. And in this cell, I would, for example, have healthy, if that's the group, dash F for female. Now imagine if you have one cell like this, healthy dash female, that would be relatively annoying because it would be non-trivial to extract all the females, all the males, all the healthy patients, all the patients with a condition from that data set. Before doing this filtering, I would need to kind of do extra manipulation and then split this into two columns. Another aspect of tidy data is that if here's my data set, here's my data set with my observations, with my variables, my data set limits itself to a rectangle. Now this is obvious if you see this data from an R perspective and this data is a data frame, but it is absolutely not obvious if you think of your data set as an Excel spreadsheet. If this was an Excel spreadsheet, you could easily add a little bit of annotation at the bottom so that one column, one variable here is a little bit longer. Sorry, can you see? Right. Or add a little bit annotation on the side, or even some description here at the top, some metadata. So as soon as we think of data like a little notebook where we record our data and add notes, this breaks this concept of tidy data. And it can become a bit of a struggle to read these kind of data into your data analysis program. So if like here your data comes as a data frame, there is no problem. But if your real data that you want to visualize lives in a spreadsheet and has this additional annotation, my suggestion would be to move these annotations somewhere else in another workbook, for example, where you describe the variables and keep the data rectangular. So the data we have here, we have proteins. One variable is protein. And this is a very long table. We actually have the same protein repeated many times. Let's call this P1, P1, P1. It's recorded many times in every row. For example, for technical replicates, A, B, C, A, B, C, it was noted. And then here again, A, B, C, if we have a biological replicate, or condition 1, condition 2, condition 1, 1, 1, and so on. Okay. So you see this protein is repeated many, many times along the table. An alternative representation for this would be that we have protein 1, and maybe another one that I have to say here is ROM, okay, like sample 1, sample 2, sample 2, so on. An alternative representation for this would be to have a data table like this. Where I have my intensities here, but each protein is repeated only once on each row, and each sample is repeated only once along each column. So this would be a wide format. This one is called a long format because it is very long, 36,000 entries. In this one, And here, for this data set, we would have more or less 3,000 proteins. But it would be much wider, as wide as we have samples, and possibly additional metadata. So this one is called wide format. And generally, in omics, in the omics field, we would use the features, the proteins, the peptides, the genes, the transcripts, your metabolites, and so on, along the rows, and your samples along the columns. So, long format, wide format. Any questions? Were you familiar? Who was familiar with the long and wide? Can you raise your hand? Okay. So let's transform this long data set into a wide data set. So the first thing I would like to do here is to kind of slightly simplify this data set. And just to focus on the variables of interest, which are here 1, 3, and 6. So let me execute this. And I'm going to focus on these 3 variables. Okay. So I subset here columns 1, 3, and 6 to on the peak protein, run, and intensity. Proteins, runs for samples, and intensity here to populate my wide data set. And how do we transform one into another? Well, to do this, we are going to use a package called, or a function in a package called tidr. So I'm going to load tidr here. And as input to tidr, I will use iprg2 that contains these 3 variables of interest. Function I want to use here is spread. Okay. So from this data set, I want to spread some variables, the samples. iprg2 is the data that I want to spread. So what do I want to spread? It's the run, the name of this column here that I want to spread, and the values I want to use intensity to populate this data after spreading the runs are the intensities. I'm going to call this iprg3 and split this line here. Pardon? I am missing an R. Thank you very much. I like that because that's how things work in real life, right? Because we've always shown slides, this wouldn't happen, but this is going to happen very often. Like starting to type in capital, I'll start typing in capital. It already has happened, and that's the reason why. Because the reason for that is because on my computer the caps lock and the shift are switched. So I will always use caps lock here instead of, sorry, not shift, control. Intensity. So it didn't complain, that's good. And well, you know what, I'm going to say view iprg3. Okay, so here it is. This is iprg3. As expected, I have my proteins along the rows, and now all my samples spread along the columns with intensities. Okay. So I would like now to check whether this worked. I would like to check whether this worked and gave me a so let's see. Dimensions of IPRG3 are 3,227 by 13. Okay. Now let's see. IPRG2 $protein. If I keep only the unique entries here, and I want to see how many of these unique entries I have, 3,027. So the number of rows in my new data set match the number of proteins I had before. And actually, I can also copy this. If I check the number of runs, 12. Yes, that is correct. I have 12 runs, but here I have 13 columns because my first column is my protein identifiers. Okay. But I would like to highlight one major difference between these two data sets. And I'm going to look for missing values. Okay. Are there any missing values in IPRG2? The answer is false. No missing values in IPRG2. Any missing values in IPRG3? And the answer is true. Now suddenly I have missing values. I converted this data table, this format, from long to wide. I hope I convinced you that I did a correct job, at least superficially it looks like it worked. But suddenly I have missing values. Can anyone tell me why?
There might be some intensity missing for one of the proteins.
Yes. But where do they come from? My dimensions match. I have the same number of proteins in one data, and then in the other one, I have the same number of samples in one and to the other. Why do I suddenly have missing values? is.NA IPRG3, which and I can see here that I have missing values in row 652, column 12, and this row, columns 2 and 3. So can anyone, do you have an idea? And, you know, visualization is one aspect of exploring data. And the point I want to make now is that different formats, long, wide, and so on, provide different benefits. So can anyone? So here I have my wide format. Here are my runs. Here are my proteins. And suddenly for one run, one protein, I have a missing value. And I didn't see that before. And that is because in the long format, there was no row for that protein and that run. It was not present. But now because I transformed this data set, I forced to have a row for each protein and a column for each sample. And so suddenly missing values appear. So it is when we have the wide format, it is very easy to check whether we have missing values in our data. In our data, all our proteins, all our samples. It is not as straightforward when we have it in long format. We have seen it, it's easy to transform from one to another, and I'm sure it would be also straightforward to find a way to manipulate that data set. Yes?
I'm supposed to do what the spread program did.
Yes, okay. So let me show here. So this is the IPRG2, IPRG3. These are the data sets as we produce them. Okay. Our IPRG2 has 3 columns: protein, run, intensity. So what spread does, and my key was the run, and my value was intensity. So spread is going to take all my unique occurrences of my key and create as many columns as we need. So I have 36,000 rows, and these 12 samples are repeated as many times as we need it. So it's going to take these unique occurrences and use them as column names. That's the key. And then it's going to take the values, first protein, first run, 11, 7, 8, blah, blah, blah. No, that's not the one. Ah, okay, it is. So that protein should be here, D6VT. My first sample, 0623, finishing with 14. It takes that value, it puts it there. So it's going to take the kind of protein ROM associated value and put it in the right cell. I have a preference, from long or wide data, but that preference only exists because I have been used to one format of data and not the other one. None is better than the other one. It's just that these different data sets allow us to extract different properties in an easier or slightly more difficult way. For example, missing values show up immediately here because we enforce to have a cell for each protein sample pair. This is not enforced here. Clearly, if you want to do, depending on what kind of visualization you want to do with ggplot 2, that is what you would want to use. Okay, so we have spread to move from a long to wide data set. The opposite of spreading is gathering. So IPRG3, so I now want to gather IPRG3. My key is run and my value is intensity. But I also need to say that I still have this protein column and I want to keep it, but it doesn't participate into the action of gathering data together. So IPRG4 So I start with IPRG 1 or 2. I move to IPRG 3 by spreading, and I'm moving back to the long format with gathering. IPRG 2 is what I started with. 3603 to 1. Dim IPRG 3. Dim IPRG 4. So as you can see here, the final rows don't exactly match. And this is because these 3 missing values that were now kept when I moved back to this long format. Does that make sense? So I'll give you a couple of seconds, and could you put your blue sticky notes if it makes sense, yellow sticky notes if you are a little bit confused. Long data format, protein ROM. I have protein 1 and 2. I have only 2 proteins. One and 2 for 2 samples. A, B, A, B. Here are my intensities. A, B, C. Imagine I haven't recorded intensity D here. I'll put it an A. In my wide format, this becomes will leave you to help me to fill this out. I have proteins 1, 2, samples A, B. What's intensity for protein 1, sample A? A bit loud. I do not hear very well, so you need to shout out loud. A, thank you. Sample A, protein 2, B or C? Oh, is that an NA? Okay. My NA is here. Sample B, protein 1. A. Okay. There is A, B, C, and A. So we are happy. A for 1, this one. 2A, C. 1B. Ah, okay. Thank you. Good. So I was wrong. I confused you. Is this still correct?
Yes, that should be NA now.
This one is NA.
Yeah.
Protein 1, sample B. And this must be power of production. Okay. Right. So here, clearly, I will have 4 cells. Whatever I do, I will always have 4 cells. And if I have one missing value, it's here. Now, in this table, I do not need to report this line. I started by writing it out, but actually, I don't need to report it. And that's why my number of rows here, I start with this. That was IPRG2. I move to IPRG3 when I spread it. And when I move back from there to there, this row with an A was added. And this explains the discrepancy I have here. So this could be processed and removed, and A.omit, for example, IPRG4. I can remove them like that, but they're in Gather. I need to check the name. Yes, in Gather here, I could also say, let me copy this. I could also, as in many functions, there is an A.rm equals true, and in that case, it would not add these rows with missing values. Okay, that had missing values over there. Okay, so that's for this IPRG data set that introduces the long and the wide data formats. So let's look at the second data set, the CRC data set. This data set, we have information for 200 samples, and for these 200 samples, these are different groups. We have healthy and cancer patients. And so we have 200 samples, and for these 200 samples, we have assayed 72 proteins. So read.csv with this biomet data. That's my kind of prefix for all my data sets. And this data set is called CRC CSV. Oh, and by the way, for those that can read it, I have written the short URLs here. It's always bit.ly. So this biomet, this with an S, sorry, CRC CSV, and so on. Oh, I forgot the IPRG. So let's view this data set. And I call it here CRCDF because it's my CRC data set, but a data frame.
Can you show that?
Yes, yes. Ah, yes, let me wait.
quick question, did you set up it separately? Because if I don't put the assets into the video, it throws an error.
If you
From HTTPS.
oh yeah, I don't know how Bitly, apparently there is no HTTPS in that Bitly.
Okay.
I created these short URLs. So these get resolved into a really long and horrible URL. And I created the Bitly short URLs, but I don't know how it manages HTTP image. Oops. So here is this data set. What we have here along the columns are proteins. You probably recognize some of these names. For me, these are obscure codes. So we have 200 proteins. Sorry, we have 200 samples. Oh, let's check. Let's check. I'm going to type here dim crcdf. Oh yeah, 200. So that's correct. 200 samples along rows, and then we have 79 columns, and that includes the 72 samples. And let me move towards the right, plus additional variables, including the sample name, what group, age, gender, cancer stage, tumor location, and so on. So this is the information that we have for all these different samples. Okay? So here, after sample, we have 1, 2, 3, 4, 5, 6 sample annotation, metadata about our samples. So what I would like to do now with this data set is to introduce a new data structure. And that's a specialized data structure for quantitative data. And to explain, to understand this data structure, we'll start with the wide format, where we have features. I'm going to call them proteins here, but it doesn't have to be proteins. And we're going to have samples along my columns. So a little bit like this data set, except it's transposed. And so I'm going to write here, because otherwise I'm going to get mixed up. And we have 72 proteins and 200 samples. Now what we have also seen that here we have metadata for these samples. But we have annotation. Each sample has additional metadata, additional annotation. So for each of these samples, I could represent another data structure with age, group, gender, and so on. There can be as many additional variables I want, but each of these variables must be repeated as many times as we have samples. Does that make sense? So this is sample metadata, or I'm going to call it phenotypic data. But there is another type of annotation that I can have in biological data, which is annotation of my features of my proteins. Here are my proteins. And each of these proteins can have additional feature data. This could be a gene ontology term for its localization, these are proteins. This could be maybe an obvious case, the description of that protein, its accession number, and so on. Can anyone give me another type of metadata that I would have for each of these proteins?
Would the number of peptides for that protein be associated, or does it have to be a constant?
No, no. That is a very good example. So this protein has been observed with 25 peptides. This, 2 peptides. 77 peptides, 1 peptide. And that is the kind of metadata I would be interested in, because maybe I don't want to rely on proteins that have been identified by a single peptide as much as a protein that has been identified with tens of peptides. Another idea?
Going off of that, I mean, various like confidence scores or posterior error probabilities, things like that.
Exactly, exactly. Another important metadata would be p-values, for example. Let's imagine, okay, I have 2 groups of samples here, and this would be reported here. So I have a group 1, and here a group 2. I can do tests, this group against this group, and this would return, for example, a p-value, or I can calculate fold changes. So these are also metadata that I have here, because every comparison, group 1 versus group 2, will return, I can compute 1 fold change, 1 more fold change, and a p-value, and then just a p-value. So these are additional metadata that can be used to annotate the features. And an important point to note here is that these metadata are part of your data. Okay? You calculate them with your precious data, and these are precious results, and it's a good thing to try to keep them with your data. Assuming, of course, all this can be stored together as one big data set. And this is the data structure that I would like to kind of follow. Yeah?
Does this data also have to be square?
Well, this data on its own will not be square. This data will be composed of a rectangle, O in Y format, that contains the quantitative values. This data will be composed of a data frame that matches the number of columns here, and another data frame that matches the number of rows here. So it's a non-rectangular data set that itself is composed of little parts that can be squares.
And I'm trying to think of this in the context of the tidy data that you were talking about.
So to answer that question,
tidy or non-tidy?
it is not tidy with the definition of a data frame or spreadsheet as I described it, but the concept of tidy data and data analysis can be expanded to different types of data sets. So it is tidy in a sense that it's well defined and well structured. And the tidy data, the more general concept is that, do you have data that is defined and structured so that you know where to get what?
Okay.
And indeed, here we know where to get what kind of information. And so this data structure is called an MSN set. And you can I'm not going to show you how to create it, that's described in the notes. That data set is called, I'm going just to write it out here, is available in the crc.rda file, and is called CRC. I'm not going to spend time describing this MSN set now, because we're going to look at another MSN set that is available in a package called Prolog Data. So if you load Prolog Data, it should actually load additional packages for you. And then if you type Mulvey 2015, it's going to load that data set for you. So that data set, Mulvey 2015, comes with this package, prolog data. And I suggest that if you have issues installing packages, when we break for lunch, we will try to install these together. Okay, so in doubt, always use class to remind yourself what kind of data do you have. And here it says MSN set. So how can we access these different parts here? EXPRS. Oh, actually, no. The data set that I want is Mulvey norm. That's the one that we'll use later on. 1, 2, 1, 2, 3, for example. So this is a matrix. It's a two-dimensional object. We use the square bracket subsetting for it, as we are familiar with. Comma, before the comma, subsetting along the rows. After the comma, subsetting along the columns. And so this is this data set. Here are the proteins, and here are the samples. Well, actually, maybe let me start by typing its name. So that is what is printed out. It's an object of class MSN set. We have 2037 features for 18 samples. And so EXPRS is what we can use to extract the quantitative data. The phenotypic data can be extracted with a function called pdata. So here it is. Here is the annotation of this data that we have. We have replicates, 3 replicates, the condition is all 1, but we have 6 time points. So this data set is a time course experiment where the development of extra-embryonic endoderm mouse stem cells has been observed. Okay? Time point 1, 2, 3, 4. And actually, if we look at the sample names, view the sample names here tell us we have replicate 1, 0, hour, starting point 60, 24, 48, 72. And then is the kind of the final stage of development, a set of 6 samples for replicate 1 over time, a set of other 6 samples, replicate 2 over time, and so on. So this is the data set that we will use to produce some sort of visualization related to the time course of this development. And I haven't told you yet how to access this last part of the data, the feature metadata, and this is done with a function called f data. So let's view f data. So this is what we have for the feature, the annotation of f data. Here are the protein names, exactly the same protein names as we have here. We have accession numbers, we have description, we have scores and coverages as were discussed, and so on. And here it becomes very easy to add as many annotations as we want. We can grow this data frame as much as we want towards the right without perturbing the other two. And all the syntax that you know for matrices or data frames to do the subsetting will also work on these MSN sets. So for example, if we want to look at the dimension of this MSN set, the dimensions are rows, features, and columns, samples. We can do the subsetting, let's say 1, 2, C1, 3, 5, and then for the 3 first samples. Okay. So the subsetting works like we have our matrix or data frame. Here is subset the first, the third, and the fifth protein for sample 1, 2, 3. Square bracket operator for subsetting with this MSN set as it was the matrix or data frame. And it will handle the subsetting of the quantitative data, the feature data, and the feature metadata, and the sample metadata automatically for you. Oh, thank you. Yes?
How can I store this large variable name into another variable? I'm trying to like copy it to another data frame, but it's not.
Yes. So, what would you like to copy to another data
So
frame?
if I want to just call it something else.
This or the whole thing?
The whole thing.
The whole thing. So, how would you like to call it?
M or something. Like
Yeah.
just give it a short name. It's not working.
Let me see.
Dimensions on this, it is none.
Have you loaded?
Yeah, it's loaded. Like the original is working fine.
Oh no.
Oh, it doesn't.
So, this command is something that you call once to load the data set. And once you run this command, then you will have, let me remove this line.
Command doesn't return the original data.
No, this command loads your data in your workspace. And once you have done this, then you call, sorry, I deleted the wrong. Once you run this, then you will have in your workspace a variable like that.
What was that you just deleted? I was trying to figure out what that class smallly data was.
Okay. Yes, sorry, I'm going to call this.
Okay, it's because it's
Yes.
norm. Okay.
There are two data sets. One is called Molvik 2015, the other Molvik 2015
And
norm.
class is that big chunk.
So class is, what class is this data set? This object in R. What type of object is it? So for example, if we ask here on the right, what's the class of CRCDF? It's a data frame. Or what's the class of IPRG2 that we created? It's a data frame. RPG3. These are two different forms of the same data set, but they're all data frames. Yes? Okay, so I suggest we will install packages. Oh, actually, to install. Could you run this line number 2 here, source, and then this, and this should install all the packages for you. It'll take a little bit of time, and then we can look at it over. And the last data set that we are going to use is the data set called ALL for acute lymphoblastic leukemia. It's a rather well-known and old data set from 2004. That's not proteomics. It's a microarray, the good old school Affymetrix microarrays. And that data set is available in a package called ALL. Yes. let me make a little pause here. And yeah, that's probably good. So typically when you install packages from kind of your usual R packages from CRAN, you would use installable packages, right? Oh, sorry, there's a question there? Oh, can you then take your red sticky note? Oh, okay. Installable packages. And that will install your packages from a CRAN mirror, you know, one of these main R servers around the world. But if we want to install packages that are specifically defined for kind of high throughput biology and so on, very often these packages are not available on CRAN, but they are available as part of the Bioconductor project. Who's familiar with Bioconductor? Okay, not everybody. So Bioconductor is a dedicated R project that brings together, that offers a set of R packages dedicated for the analysis and comprehension of high throughput biology. So for example, for those that were last week in the advanced R programming course, you have learned object-oriented programming, you have learned package development, among other things. Well, once you have, or if you want to implement the package, and you want to disseminate it, to distribute it among the community, or if you want to write a paper about it and disseminate your package that specifically deals with one area of high-throughput biology, then you could submit it to Bioconductor. And after review, in addition to the project, everybody will be able to install your package, as I'm going to show now. And a lot of these packages that we're going to use, for example, the MSN set class comes in a package called MSN Base. People in the other room are learning kind of statistics for proteomics, and they're using Bioconductor package called MS Stats, and so on. These packages come from Bioconductor project, but they are not installed using installer packages, or at least under the hood installer packages called, but not as users. And so to install Bioconductor package, the very first step we need to do, and that's only once, is to type source. We need to source this file only once, and that line of code will download the package and install it for you, and that package is called BioC install. And that's a package that will allow you to install Bioconductor packages as its name implies. Now the reason why you can't use installable packages is that Bioconductor is a structured project, kind of globally maintained project, and it's tied with a specific version of R. If you use installable packages, whatever version of R you have, you will get the latest version of that package from CRAN. With Bioconductor, that's not the case. Specific packages are tied, or a specific version of Bioconductor is tied with a specific version of R. And that's why we need to use BioC installer, and the function is called BioC Lite from that package. So to install the package ALL, I would say BioC Lite ALL, and essentially the same things that would happen with installable packages. The only difference is that here, BioC Lite knows that it needs to download the package and its dependencies from the Bioconductor server and not any other CRAN mirror. So now that ALL has been installed, I can load ALL. And the reason I want to introduce this data ALL is because I have pre-analyzed, pre-processed this data set. to download into another Amazon set that should be available in this this data.zip file. And I'm going to download it here. This biomet data ALL underscore. And this data set has been somehow reduced. We don't use all the groups, all the samples in the original ALL data set, but only the BCR negative kind of samples. And so this URL here will get you immediately this modified, reduced data set. And the download.file function in R takes two arguments. The one is that the file that we want to download, and the second one is where we want to put it. And I will want to put this data set in my data subdirectory that I created as part of my R project. And I will want to call bcrnec.rda. Yes. And so here I have a subset of this ALL data, and in the notes, and I can show you during lunch how we have done the subsetting of this data set, large ALL to the subset ALL. But the reason, the real reason we are going to use this file, ALL Okay, somehow that file is corrupted. Could anyone try for me, please, to download the file as it is here, and then I will repeat the analysis during lunch. Well, the real so if anyone could run this command that downloads this file into this directory, that file.
What if we had we don't have that directory, the .data, just because we did it somewhere else? How would you tell it to go to the desktop file that you have all your things on?
Yeah. So you would do it like this, then it would download that file in your working directory.
So that's what I did.
Yes.
But then it's telling me that there's an error or something like that. That's exactly what I did. So I downloaded it, and because I didn't have that, I had a working directory. And then
Yeah, so the file, so the download was successful.
yeah.
But what you need to load is ALL underscore
Oh,
BCR.
BCR. Oh, it's a little thing, sorry.
ALL is the full data set.
Yes, I want to do the BCR.
Yes.
Sorry.
And the reason we are going to use this file, this data set, is because I have already done the statistical analysis. And so this data behaves, it's technically speaking, it's not an MSN set, but it's an expression set. As far as we are concerned, it's the same thing, but expression sets are fine-tuned for microarray data, and MSN sets are fine-tuned for proteomics data. They have slightly different behaviors with the understanding of what kind of data they store. So we can use EXPRS like we did before. So these are microarray probe sets, and these are the samples. We can use pdata, and I'm going to use view here to show you what sample annotation we have. So our sample names are here. This is what we find back here. And so we have sex, age, whether there are emissions, and a lot of metadata for these. How many? Let's check. Dimensions. Okay. 128 samples, and we have 12,000 probe sets, 12,000 features in this ALL. And in the ALL underscore BCR NEC, one of the feature data that we have here are p-values, log4 changes, and adjusted p-values. Okay. Properties that tell us if there is differential regulation between ALL patients and those and healthy patients. And these p-values, these are just p-values, and these log4 changes are those that we are going to use in the session where we'll look at visualizing results of statistical analysis. So what kind of things are we going to do with all these data sets? This figure kind of summarizes a typical workflow that we have in proteomics. When we start with raw data, we quantify and identify that raw data to obtain quantitative data, expression data. This quantitative data is annotated. That's an extremely important point of any experiment that we have. We have sample annotation and feature annotation, as I showed here, that we will need, for example, to do exploratory data analysis, to do statistical tests. And already here, at the metadata level, we can produce bar plots and tables to try to understand our data. We will also have QC plots, quality control, on either raw data or on the quantified data, where we have kind of opportunities for visualization. And then we have a whole set of data analysis that we can do on this quantitative data. We'll want to normalize these data and visualize the data before and after normalization using box plots or density curves, for example. We'll want to look at the variability in our data, for example, within a group and between groups using scatter plots or box plots. We'll want to kind of verify our experimental designs, replicates and groups in our data. How can we do that, for example, using heat maps or Pca plots and dendrograms? We will produce many of these. We might want to look at missing values or patterns of missing values in our data, differential expression, and gene set enrichment. And so here are some of the data set, some of the visualizations at these different levels that will be, I'll show you how to do, and some of these you'll do yourself. So for example, when we have raw data, we might also, here we have 3 files, we might want to look at the total ion chromatograms of these 3 files, either total ion chromatogram here, or the base peak chromatograms. Do we see discrepancies between these different raw data sets? We might want to, so this is an animation that has been produced by kind of parsing raw data. And the animation as such is not scientifically very revealing, but it points out that by accessing the data and knowing where to access what part of the data, okay, we can control it to the extent that, for example, we could produce this an animation. And this is a kind of a mass spectrometry map where we have here retention time, the ions that are used over time, the M over Z value, so these are the scans that we see, and that are, the ions are measured at certain intensities. Being able to access the data in a specific format allows us to really track an ion of interest. So at a certain point at the retention time here, after 30 minutes, here's an MS1 spectrum. with a set of ions that were selected for MS acquisition. So these 10 ions, MS1 spectrum, acquired at 30 minutes. Here it is. And then 10 ions were selected for MS. Here are the 10 MS spectra for MS1 spectrum. And here's the isotopic envelope of one of the ions. This is the kind of visualization that, if we wanted, we could generate. Here's an example of a QC plot, where we take all the MS spectra, or a fraction of these MS spectra, and calculate the differences between all the peaks, the MS peaks. And if the majority of these spectra and these peaks stem from peptides, we expect to see, and here we produce a box plot, sorry, not box plot, histogram of all these delta M over Z values. We see an enrichment in amino acid masses. If we had, for example, a big contamination in PEG, we would see a really high peak for this, for the M over Z value corresponding to this contaminant. This is at the raw data. In terms of experimental design, what data set is this? I think that's a CRC data set, where we have females and males, and these have been kind of binned into different ages. So here's a table that allows us to visualize our experimental design. So you have, oh no, it doesn't. Okay. But these extracting or manipulating the CRC data to produce a summary table also allows us to produce these kind of figures, where we have histograms for age, male and female, and CRC and healthy group. So for example, this figure was produced with ggplot2 using the CRC data frame that we loaded in a little bit earlier. Still using ggplot2 that we'll see in the beginning of the afternoon. This is the IPRG data set, our 3 replicates, technical replicates, biological replicates as standard bar charts. So we see that we have a very similar number of observations for technical replicates. This is a principal component plot of the MOLVI data set, where the different colors here represent the time points. And so on this PCA plot, we see that the time points 1, 2, 3 come together, and then time point 4, 5, and in black we have the Zen, the last part, the fully differentiated state. And the numbers within the points here are the replicates. So, considering an experimental design and producing the PCA plot, we can somehow validate whether the data as it was acquired matches our experimental design. And of course I used this example here, which by the way, if you remember, is the normalized data set. But I use this example here because the clustering in these 2 dimensions here, PC1 and PC2, and we'll see PCA analysis, how to do it, but also how it works, matches very nicely our experimental design. But this is not always the case, and there might be good reasons. I mean, there might be worrying reasons, like a big batch effect, but there might also be biological reasons why, the natural clustering of our samples don't fit our experimental design. And visualization can help us in doing that. Same data set here, MOLVI, where we create a heat map with the clustering of our samples at the top, clustering of our features, the proteins, on the side, with some color codes to reveal different time points, and here's some clustering, k-means clustering, and we'll do that together to identify some structure in features. So we'll have, as part of the tools and plots here, we'll see principal component analysis, we'll see clustering, and we'll see k-means clustering. Hierarchical clustering and k-means clustering. In terms of quantitative data, as I mentioned before, distribution of my quantities or my samples along my x-axis, before and after normalization. Being able to visualize it before and after will give you some sort of indication whether your data needs normalization and whether the effect of normalization meets your expectations. These are produced with a function called box plot. Back with the Mulvey data set, looking at the distributions of the 18 samples. So these are the distribution of these intensities, the smooth distribution. 3 samples here have slightly different set of distribution of intensities. And I bet this corresponds to the Zen data sets. Still using ggplot2. Set of report ions here, set of samples. And all the peptides, so all the MS acquisitions for certain peptides along the rows, and along the columns here we have different types of quantitation of our report ions. Starting with the data frame and using ggplot2. Here's an exercise that I would like you to do tomorrow using the Mulvey data. So times course experiment. One of the things that I couldn't be bothered here to fix is the annotation of my x-axis. So we can't read the sample names. And Stephen will give you advice on how to fine-tune these plots to make them kind of more visually appealing and more useful. But as far as I was concerned, that gave me a good indication of, I know that I have my first time point, second time point, and my last time point, and replicates next to each other. So this is also the result of doing a k-means clustering. So I asked my clustering algorithm to identify 16 clusters, and they all represented here in different sub-parts of the plot. And then kind of visualized with a smooth general trend over time. This is a Pca plot, but where each point represents one protein. The previous Pca plot we had, each point represents one sample. So we can look at our data sets, kind of like this, or from the top, depending on what we want to do. This is a spatial proteomics data set, where we want to localize proteins within a specific subcellular localization. And this Pca plot is annotated not with sample information like time point, as we had before, but each color here represents a cluster of proteins that live in the same organelle, using principal component analysis, but to reduce the dimensions along the protein dimensions. Kind of heat map type of visualization with samples and proteins, and black values represent a value, a cell with an intensity, irrespective of its intensity, and white represents a missing value. And quickly, to finish before lunch, once we have a differential analysis, and this is this ALL BRC NEC data set, okay, how can we visualize the results of this statistical analysis? For example, here the p-values. Even though this is not the kind of figure that you would put in the data, but this is the kind of, in your paper at the end, but this is the kind of figure that is extremely important for you to kind of QC your statistical analysis. So these are all the p-values that we obtain for the 12,000 or so features. Looking at the distribution of these p-values is really important, and having here a higher proportion of small p-values as opposed to uniform distribution. So we'll see how to produce these plots and how to reason to think about these plots. And still considering differential expression, maybe this is the kind of figures that you would put in your paper. Maybe you will want to use ggplot2 instead of base plotting with a volcano plot, where each point here represents a feature, transcript, or probe set in this case. And on the x-axis, we have the log2 fold change, and on the y-axis, we have to adjust minus log10 of the just p-values. I'm showing you the features of interest. And features of interest are typically those with a high effect, so large or small log2 fold change, so towards the right and the left, and those with a smaller p-value, and a small p-value means a large minus log10 value. So those of interest are those that are towards the top left or right corner. And it's I'm 5 minutes late. I'm sorry about that. But at least we managed to finish these two. I think I have been a little bit fast. So if you have questions, I will be waiting here for you. If we need to install packages, or you have additional questions about the R syntax, please come and meet me.